So 3.2 is called integration by tables. The notes start out by saying this. We have seen that in integrals of the form integral of f of x, g of x dx, in which f can be differentiated potentially repeatedly to become 0 and g can be integrated repeatedly to more or less remain the same, are prime candidates for integration by parts. However, if many repetitions are required, the calculations can become cumbersome. In situations like this, there is a way to organize the calculations that saves a great deal of work and time. So, what that's basically saying is that integration by tables is integration by parts, but for when there might be more than one round of integration by parts necessary, this, you're just going to love, this integration by tables sort of routine. Like someone at some point must have found some pattern in the repetition in all the integration by parts formulas, and came up with just like an amazing little trick here that has become known as integration by tables. Like this one, I don't know if you can kind of imagine in your head, how many rounds of integration by parts would be needed. Like you'd let u equal x squared, but then after one round and like basically one derivative of the x squared, it would be taken down to like just x to the first power. But then we would need like another round. So this would require 2 rounds of integration by parts, which is not, I'm sure you don't love doing that, but it's not like that bad. But can you imagine? It'd be very, very, very easy for me to give you an example of like x to the 5th power times e to the x dx. And that would require 5 rounds of integration by parts to slowly take x to the 5th power down to, 0 basically, to where the integral was actually, doable. So integration by tables, you're going to love it. So here's the routine, okay? And again, just to repeat something important, I guess, no pun intended, this integration by tables technique really, really, really comes in handy, and it's really only useful when you're going to be like, what does it say? If many repetitions are required for this f of x, to kind of differentiate it repeatedly down to 0. Anyway, let's just get to this example. So you're going to make basically 2 columns. So this first column is like what you would let u equal, basically what you're going to be taking the derivative of. And over in this column is basically what you'd be letting dv equal, what you're going to like essentially repeatedly take the integral of. So over here in this column, you take the derivative, which is 2x, take the derivative again, which is 2, take the derivative again. So you keep taking the derivative until you get down to 0. Over here, we keep integrating, and this one is very, very, nice and simple, because every single time you take the integral of e to the x, you're just getting e to the x. So and then you go down as many, rows as is what over here, how many rows it took over here to get down to 0. And then the rest of this integration by tables routine is you draw these slightly downhill arrows from like the top one in this column to like one level down over here, and then connect these with an arrow, connect these with an arrow or with a line, basically. I guess it just could be a line. And then this first one is plus, and then it alternates. Plus, minus, plus, and that's it. So there was no line here because, like, what are you going to go? There's nothing for this 0 to connect to. So there was 3 of these lines or arrows, and it went plus, minus, plus. And basically, that's getting you the answer. So like x squared hooking up with e to the x, and along with this positive sign, so it's a positive sign when you basically multiply these two together. Oh, of course. And so you get positive x squared e to the x from like these two hooking up. And then the next term is these two hooking up with a negative. So negative 2x e to the x. The third term before the plus c, we're always ending with the plus c, is, you know, these two multiplying together with a positive sign. And that's the answer, you know. So if you basically take out all the time I spent explaining it or talking about it, this goes like really, really, really fast. Way, 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 way faster and way easier than if you would have done, you know, integration by parts, you know, manually, like twice, like 2 rounds of integration by parts formula, because this is the final answer. Okay? So gotta love integration by tables. One more example. Integral of x cubed, okay, I mean x to the 3rd power. That would basically mean you would have like 3 rounds of integration by parts. So integration by tables is really, really, really coming through. So like you probably guessed, like we're going to be taking the derivative of x to the 3rd, and we're going to be taking the integral of the sine of 2x. So this left column, leave some space, just like don't write it like too close, like right underneath. You know, leave some vertical space. Take the derivative again, take the derivative again until you get to 0. Okay, finish copying that down. Over in the second column, we're going to be taking the integral. Now, what is the integral of the sine of 2x? Technically, you would need to do u substitution, right? Technically, it'd be like, okay, let's let u equal the let's let u equal 2x, you know, but with all the steps of u substitution, you know, isn't there going to be like, what, a 1/2 that sort of gets created and you know, inserted into the mix here? Like maybe in class already, you know, like at some point in the recent past, like maybe I've mentioned, you know, how integrals like this, even though they're technically, you know, u substitution, maybe we've gotten some practice, or maybe I've talked about like getting to the point where you can do these in your head, you know. So the integral of the sine of 2x is negative 1/2 cosine of 2x. And again, technically this is from u substitution. So what if, again, now we have to integrate again. So what's the integral again of this? You know, once again, it would technically be u substitution. You know, you'd let u equal 2x, you'd get like another 1/2 kind of in the mix. And so we'd end up with like negative 1/4 sine of 2x. And then when we integrate again, we'll end up with positive 1/8 cosine of 2x, because like another 1/2 multiplied out in front of here and stuff. And then integrating one last time, we get positive 1/16 sine of 2x. So that's all the integrals. And then we do these lines or arrows. And again, it's plus. Always starts with plus. And this is just kind of hooking up the terms of our answer. So with this negative here, you know, like positive, negative, you know, so it's negative, right? But this pretty much creates here a double negative. So multiplying 3x squared times this, and overall it's going to be positive. Here it's going to be another positive when we do 6x times. So this 3/4 came from 6/8. 6 times 1/8, 6/8, which reduces to 3/4. And then this right here, we're going to have like 6 times 1/16. What does that reduce to? 3/8, I'm thinking. And then the sign is minus. And that's the final answer. And that saves you the trouble of doing 3 rounds of integration by parts. So integration by tables, an amazing, 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 tool to have in your toolbox. Oh, and before I end the video, I should probably mention something probably important to say here. When you think back to all the other, all the different types of examples that integration by parts can be used with, like if you think back to section 3.1 for us, there was like other examples of sorts, like there was a natural log example. So unfortunately, if you're doing a natural log example, like from section 3.1, integration by tables won't help you. So sorry, but if there's a natural log involved, you have to just straight up do integration by parts, which if you remember, isn't bad at all. And it's really just going to be like one round of it. So no integration by tables there. And then the big juicy example from section 3.1, where it'd be something like integral of e to the x sine of x, and you after going through 2 rounds of integration by parts, you basically just wind up with the same integral you started with. Then you have to like add it to the other side, all that stuff. So integration by tables will also not bail you out of, for like those kinds of examples. You're still going to have to do that whole double round of integration by parts and, adding it over to the other side, to the left side, and all that kind of thing. So again, integration by tables only really applies and helps when there's going to be like multiple repetitions of like taking the derivative of something like x to some power, and you're slowly getting it down to 0. But hey, it's more than enough to be happy about.